So we have an exciting second session of the day, and our second keynote speaker today is a data scientist, statistician, experimental physicist, teacher, software engineer, and a trail runner. She has received the 2025 European Physical Young Experimental Physics Award for her instrumental work on real-time inference and anomaly detection for new physics searches. She is a fellow at the Institute of Particle Physics and Astrophysics at ETH Zurich. She holds a PhD in particle physics from the University of Zurich and has worked as a research fellow at CERN in Geneva before moving to ETH. Let's give a warm welcome to Thea Aarrestad. Her topic will be pushing the limits of real-time ML, nanosecond inference for physics discovery at Large Hadron Collider. The stage is yours.
Thanks a lot. Perfect. Oh, where can I change the slides? Here. Perfect. Great. All right, so thank you very much for having me. It's my first time at Women in Data Science. I really enjoyed the morning, super great plenary talks, really cool posters, so it's fantastic to be here. I'm going to talk about real-time inference, as was just said, specifically at the Large Hadron Collider at CERN in Geneva. So every day, I think about how we are in this tremendously cool time, in this new age of hyper-productivity. After the personal computer, this rise of LLMs is truly crazy. I remember being a kid in primary school, taking out all our 80-volume lexicons to look up stuff for my project work. And now I spend 20 seconds on GPT, Googling, give me all the references on Hebbian learning. It's super cool. And the reason we're here today is really just because of two reasons. So the PC was silicon transistors, made possible due to silicon transistors. And LLMs, big AI, is made possible due to compute and big data. As Ilya Sutskever said at NeurIPS last year in his Test of Time keynote, today has been made possible thanks to extraordinarily large neural networks trained on large data sets. Big compute, big data. Now, at the CERN LHC, we have had big compute and big data for way longer than this revolution we're seeing today. So the first computing cluster in the world was based at CERN. The internet HTTP protocol was invented at CERN for a way for us to share information, big data fast. And we had big data, have huge data, will have massive data at orders of magnitude larger than what we see in industry. So on this diagram here, you can see different size blobs. That's the data set size. For instance, Instagram content, 68, can I point? Yeah, 68 petabytes of data per year. Amazon storage, 500 exabytes per year. At the CERN LHC, we produce 40,000 billion gigabytes of data. And this is obviously way more data that we can read out and store and use. So we actually have to compress this data to a feasible data set of 160 petabytes of year per data within a very short time scale. So we've been pioneering processing huge data in real time. So what are our real-time constraints? If you look at this diagram here, you can see on the y-axis how much data goes through our system. On the x-axis, how fast do we need to be to process that data? Here you can see Netflix down here, latency requirements and throughput. You see the Google Cloud. And this is us, the Large Hadron Collider. So we have way much more data going through our system, and we have way less time to process that data, which has led to us having to pioneer real-time processing. So where does all this data come from? So here you can see the CERN Large Hadron Colliders at the border of France and Geneva. This is the Lake of Geneva. I work here at the CMS experiment, where our previous speaker, Nadia, also used to work. We were colleagues together there. Our experiments are based 100 meters underground. And what we do there is that we accelerate charged particles, protons, to almost the speed of light with very powerful magnets. So at any given time of data taking, we take data only in summer, because in winter we are forced to shut down because we use as much power as the whole city of Geneva. During data taking, we rotate 2,500 bunches, this is a bunch, containing 1 trillion protons per bunch, and they rotate at 11,000 times per second. And we need to keep this on a circular path using magnets, and we kick them with an RF radio frequency electromagnetic field to speed them up. Now, once these particles reach one of the experiments, like CMS or ATLAS or LHCb or ELISE, we again use these superconducting powerful magnets to squeeze these bunches tight together and bend them to meet each other in the interaction point inside the particle detectors. On average, 60 proton pairs will collide with every crossing. So out of a trillion, roughly 60 end up colliding, because most of it is actually air. And they're spaced with 25 nanoseconds. So every 25 nanoseconds, our camera needs to be ready to take another snapshot. And what are we taking a snapshot of? Well, every time these protons collide, the energy, this almost speed of light that we have given them, has given them a high momentum. Their energy is converted to the mass of new outgoing particles. What particles do we want to produce? The Higgs boson, new physics beyond the standard model. So this is what we want to do. The problem is, in order to get such a picture of every collision, we need to process 1 megabyte of data per collision. With 1 billion collisions per second, that's a petabyte of data every single second. So that's the whole Netflix library, more, every single second. Everything that's uploaded to YouTube in 24 hours, every single second. In a cavern, 100 meters underground, that's radiation shielded. So we have a petabyte of data every single second generated. Now, if we want to read out all that data, what does that mean? That means we need to put powering cables inside that detector. We need to put ASICs, tiny chips, to acquire the data and send it out. Now, what does that do to a detector? It makes the detector useless, because the detection material, the silicon, has been replaced by material cables, basically. So we cannot read out a petabyte of data every single second, because our detector is destroyed. So what we do instead is, this is our detector. This is the CMS experiment. Here you have the beam pipe. Protons come from this side and this side. They smash together in the middle of the detector, and they shower through the experiment, and we try to measure the properties of these particles. A collision happens here. The data from that collision just hits in a detector are stored on tiny chips inside the detector. Now, those chips are tiny, so we can only afford to store the data for currently 3 microseconds, so very short. When 3 microseconds is finished, the data falls off the chip, and it's lost forever. So we have to finish all our processing within that time. We have these high-speed optical cables that lead to a radiation-shielded cavern right next to the detector. Here we have 500 field programmable gate arrays. It's like hardware that has the job of acquiring that data. Again, this computing farm is located 100 meters underground, right next to the detector, because if we send data up, we've lost all our microseconds, basically. So there's no cloud compute, there's no sending data in and out. It's high-speed optical links going from detector straight into the fabric of the FPGAs. So the data we send out is 63 terabits per second. That is 5% of the total internet traffic. Again, 100 meters underground in this little cavern. Here we have the impossible task of reconstructing all of what happened here, and then make a really fast decision on whether or not to keep that collision. We can only afford to keep 1 out of every 100 collisions. So 99 of 100 of every collision we have to discard, because we cannot read it out. And we have to do it within the buffering time, because the collided information will fall off the edge if we don't do it within that time. And here we have these 500 high-scale, expensive, 10,000 euro Xilinx FPGAs to do this job. This huge system gives one output, a 0 or a 1. If it's a 0, we reject the data. We say, flush the pipeline. The data is lost forever. No human will ever have interacted with it. If it's 1, if and only if it's 1, do we take the data, the full data, and send it out of the detector to the surface? So here we have 99.72% of the events rejected. They're gone within these 3 microseconds. We're sending out 110,000 events per second at 100 gigabytes per second. Now, we still don't have the compute power to reconstruct all of this data or store it. It takes 20 seconds per collision event to reconstruct the event. We cannot do it. So we send the data to the surface, where we have 30,000 CPUs and 400 GPUs, so heterogeneous cluster, with a latency of 300 to 400 milliseconds to reject a further 99% of the 1% we actually sent up. And here we are in the self-driving car latency domain of milliseconds. So for us, we have heaps of time. So there we have way less back pressure, so we have 300 milliseconds or so to analyze that collision data. Then and only then do we send that data for offline storage and reconstruction, rejecting 99.9975% of the events. We're at 1,000 events per second, 5 gigabytes per second, and that's the data we have to do any sort of physics search at the LHC. So that's what's remaining. What we want to do is to do highly precise measurements of the parameters of the standard model to a 5 sigma level. So what that means is that every single piece of data is important to us, and we need to measure it extremely precisely. So that means in order to do a discovery plot of, say, the Higgs boson, this is the Higgs boson discovery plot, 10 collision events was enough to claim Higgs boson discovery out of trillions of colliding protons. We need to make sure we select the right 0.025% of data, so we have to be extremely fast, get more data through, and extremely accurate to select those right 10 events to claim the discovery of a new particle. So this is kind of difficult now. In the future, in 5 years, we have an upgrade called the high luminosity LHC. So here you can see in a 6 centimeter spacing, it's roughly this size of your pinky finger, every single yellow dot is a proton pair that collides. Every single line is a new particle that was produced. Out of these 60 pairs, we choose one that's interesting, that has the highest energy coming out of it, and we reconstruct tracks coming out of only that one, particles coming out from only that one. In the future, we will have 2 trillion protons per bunch. We will squeeze the bunches tighter together, so on average, 200 of these proton pairs will collide in one cross-section. And we still need to select only one, and select only the particles coming from that one. So the future for us is terrifying. We will have more data, but the data complexity is huge. So right now, we are really redesigning the whole event filtering workflow to be able to cope with this environment. How will we cope with it? With machine learning, task inference on specialized hardware. On software, we have the heterogeneous computing farm, where we do GPU inference with latency of 100 milliseconds or so. And here we use kind of commercially available tools because the latency is long enough. We have millisecond timescales. We use Triton. And this I won't talk about in this talk. But here, underground, we have a latency of 1 to 25 nanoseconds to do processing inside the detector, because we need to process the data before we even send it anywhere. And we have latencies of 10, 100 nanoseconds on the FPGAs. So this area, we have had to develop tools completely on our own to tackle this. So how do you write computing code for these type of environments? So what we usually do is we do what's called we write code in high-level synthesis. So usually we write some C++ code with some directives for a compiler. That compiler is vendor-specific, so these are different types of FPGAs from Xilinx, Intel, or ASICs. You can also print silicon. You send that C++ code with their constraints and directives to the compiler that does the compilation into hardware description language that gives you a firmware block out. There are commercial tools to do this part, but every single commercial tool that we tried was way too slow for us. We couldn't reach nanoseconds latencies. So what we had to do was redesign this whole workflow by ourselves together with AMD in tools called FIN and HLS4ML. So how does this work? We start always with a model, and that model is quantized and pruned. We'll talk more about that later. So it's reduced to its minimal size. And we support all sorts of front-end library and different quantization libraries I'll talk about later. Then that model is passed to us, our software library called HLS for machine learning. We convert the model to an internal representation that writes that C++ code for you with the correct pragmas for your compiler, the right constraints. You can emulate that firmware code completely in Python. Imagine you would have to write your FPGA firmware and then test that. It would take you ages. Here you do everything in software, and you can build the firmware. And you can have that running on a co-processing kernel. Let's say you want to do inference on your CPU, offload something on the FPGA. You can use accelerators. We support that. FPGA custom designs, like we have a full FPGA cluster, or you can even print ASICs, silicon, using these tools. And here you can see an example. So here you have a CNN trained on MNIST to do digit classification. There's a very small network, convolutional neural network with a softmax output. So and this is the floor plan. So here you can see how each layer maps out onto the FPGA. This is a tiny FPGA. So we call our framework, or this code, a data flow architecture. It's inherently different from a von Neumann computer. So a von Neumann computer is kind of sequential, it's decided ahead of time, what will run when. In a data flow architecture, everything is based on availability of data. So as soon as data is available for a given operation, the operation starts. So minimum latency is a data flow architecture. Every piece of hardware is tailored for a specific model. If you run on a TPU, a DPU, an AI engine, that is generic firmware. It will work for any model, but it will be slower, and it will use more resources. Here we tailor the hardware for a specific model. Importantly, every single model stays fully on chip. The latency you have in inference comes from data transfer. So if you send data to off-weight, off-chip memory and back, you've lost your nanosecond, so you can forget about it. So decisions are design time. Nothing happens at inference time. This FPGA, which you can also notice, is completely full, and most of it is taken by the softmax, which is actually a pre-computed lookup table. So for us, the main challenge is that ideally, we want to put a big transformer on that FPGA, but in reality, it needs to fit within the constraints of the chip. Now, we have been forced to think about how we can reduce these model sizes. And now, in LLM land, everyone is looking at efficient inference as well, because I have a really nice quote from Lidong Zhu, the VP at Microsoft, also from NeurIPS last year. We know that you cannot scale a system by throwing hardware at it forever. The bigger the model is, the more hardware you throw at it, small inefficiencies become visible, and failures start happening. So you need to start being smart in how you design models. You carefully, in GPT, for instance, they carefully map every layer of a model onto a piece of hardware to make it fit and to be efficient. So we need efficient models, and we need them now. And the main ways people deal with that is through quantization, through pruning, to parallelization, and knowledge distillation. And the biggest power by far, of course, this part in the hardware, but quantization, as you've seen in these low 1.58-bit LLMs, is really the biggest trend right now. So what is quantization? So every time you train your model, you train in floating point 32 precision. You have a huge dynamic range. You have very fine granularity. Great. Now what we want to do on hardware is use fixed point precision. So for instance, for a bit width of 4, this is here the bit width of 4 and 0 integer bits, you can have 2 to the 4 or 16 buckets that you put your numbers into, and the range then goes between almost -1 and 1. Now, why do we want to do that to our weights and biases and activations? The reason is, if you look at the number of giga operations you can do for a floating point 32 model versus something that's binary or at 4 bits, you can have trillions of quantized operations if you quantize, and it's a really easy thing that you should do. If you run on a GPU, int 8, int 4. Also, you can fit way bigger models. You can take the on-chip weights from 2 million to 64 million, a factor of 30, and you can stay entirely on-chip. So we want to do this. The problem is, if you reduce numerical precision, once you get really low, if you look at the accuracy, you basically have a coin toss less. You're training floating point 32, you quantize, of course it's lossy. So what we do instead is what's called quantization-aware training. In quantization-aware training, we have quantizer function that during the forward pass puts the number into little buckets. During the backward pass, everything is done in floating point because it's non-differentiable, this quantizer operation. It's called the straight-through estimator. And here, the network will adapt to whatever precision you have on hardware. It's called hardware-software co-design, basically. And this is really easy. For those who've played with Keras, you add a queue in front of your dense layer, and you pass a quantizer. For instance, here you have a bit width of 6, 0 integer bits, and the network learns what precision it'll have on hardware. Here you can see a little bit what such quantizers look like. In blue, you have a normal ReLU, quantized bits here. You can see you have these 16 discrete buckets, values a weight can take. You can quantize in powers of 2, so you have small ranges around 0, and then wide as you go out from 0. And you get really cool models this way. So please don't look at all the numbers. I'll guide you through some things. So here we, for instance, have a model with a 4-bit layer, a ternary layer, one where the weights are binary and the bias terms have a bit width of 8. And what's cool is that if you look at the energy consumption relative to a homogeneously 6-bit quantized model, you can get a third of the energy consumption. The size of the model on firmware compared to a model that's been quantized to 6 bits, so very small, int6, you have a fifth of the space used on the chip, so really powerful. You can even optimize this in a search, a hyperparameter optimization. So here you can see the Pareto frontier of the accuracy versus the bit size, varying what precision you use for a convolutional layer, and at the same time optimizing the number of filters, because that will also inevitably change if you change the precision. Okay, finally, everyone is talking about transformers. Big shout out to decision trees. So what we still keep seeing is that decision trees outperform deep learning on tabular data in almost every single case. So this paper is from one of the founders of scikit-learn, and he just at NeurIPS showed a paper where he finally managed to outperform a decision tree with tabular data. So decision trees are awesome. Always try them first if your data is tabular. 60% of inferences in Google are also decision trees after you're doing AutoML. The benefit is on hardware. If you go from a quantized 6-bit model, you can get the same accuracy, but a fraction of the latency and a fraction of the resources using a decision tree. So it's great. So finally, to end, where are we using these things at the LHC? First, we need to do machine learning inside the detector. We have a megabyte of data per collision, and we can only read out 200 kilobytes to the level 1 trigger. In the future, we have a great new high granularity calorimeter with 6.5 million readout channels, is a factor of 10 more than what we used to have, and a depth of 50 layers. The problem is that we cannot read out all that data fast enough. It's too many channels. So we need to compress the data on the detector. This detector is in a high radiation environment. Everything is cooled to minus 30 degrees, so it needs to use milliwatts of powers. And we need to do the processing within 1.5 microseconds. So what we do there for data readout is using machine learning compression with variational autoencoders. So we train an autoencoder to compress and decompress that data, basically encoding the data in a lower dimensional embedded space. What we do then is that we put half of this network, the one that does the encoding, on an ASIC inside this radiation environment. And then we transmit the encoded data to this level 1 cavern. And at that level 1 cavern, we can decode it again if we want, or we just operate on the latent space directly, which is probably more efficient. This was really difficult. We needed to stay within 100 milliwatts of energy, so this network is actually 75 to 100. Every single weight and bias is triplicated, because if there is a bit flip due to the radiation, we know exactly what the weight of the number is. So everything is triplicated, and we can reprogram the weights and the biases. We even have a library called fault QKeras that can estimate which part of your network is most sensitive to a bit flip, so relevant for satellite applications where you also have high radiation. We're also using machine learning for reconstruction and decision-making on FPGAs. We will have 40 million inferences per second during high luminosity LHC. One example is we're changing completely the way in which we select events. So before, we would look at a particle's energy and say, OK, only high-energy particles are interesting. But of course, new physics, interesting phenomena, can fall below that threshold. So here, we are using machine learning to do things differently. We're using anomaly detection to rather learn from the data itself what data is normal, learn the PDF of the data, and select everything that is abnormal. Again, we do this using autoencoders. We start with our collision data. We compress it onto a lower dimensional embedded space. Here we do it variational, so instead of just neurons, we have a mu and a sigma, which is a Gaussian that we then sample from, and try to reconstruct that event. Now, if new physics comes in, which has not been part of the training set, or in a very low fraction, this compress-decompress flow will fail, and we get basically trash out. So the difference between input and output can be used as a metric to say what's anomalous and what's not. It's often used for financial fraud. I guess some of you are here from banking as well. So we cannot fit this whole network because this takes 100 nanoseconds. So what we have to do instead is do inference in the latent space using the mu's and the sigmas. So we could half the network, have 50 nanoseconds latency, that was our constraint, and then select events that are anomalous. Finally, we also do other stuff. We have anomaly detection currently running, selecting 300 anomalous events per second. We can do interaction networks and deep sets in less than 160 nanoseconds. We can even do fully on-chip transformers in 90 nanoseconds. So this is really cool. We also work outside of particle physics. We've been working with Volvo company Sensact on semantic segmentation for self-driving cars, seizure predicting brain implant to detect epilepsy attacks before they happen and trigger an alert, and Earth monitoring for plastic waste in the Earth's ocean on satellites, and many, many more things. Fusion science, crustal structure, accelerator control, etc. Finally, industry is even helping us. So Siemens got a request, or they asked us if they could implement a backend for us. So basically, a way of making chips using Catapult, Siemens Catapult library. So also industry is really interested in our software as being one of the best that are out there. So that was it for me. Before I leave, I want to advertise the Fast Machine Learning for Science conference. If you are interested in efficient training, efficient inference, real-time inference for science, please send an abstract submission for a talk, a poster, a tutorial, and join us in September at ETH. Thank you very much.
Thank you very much for a very insightful talk, and it's very exciting, and you take the efficiency to the extreme, I guess. Yeah. So now it's time for questions. I wonder if anyone from the audience may have some question to ask. There is one over there, if someone could deliver a microphone. Thank you very much.
Could ask two quick questions, but I'll start with the second one. So how good do these methods work in a nutshell? So I don't know if you have any comparison, like before AI came into play and now of course the throughput is much better. Yep. But do we manage to detect interesting things more than previously?
So for some of the applications we have, what we are really just doing is enhancing signal over background. So let's say we have a variable we're interested in, we can improve the resolution of that variable by a large amount. And there we really see up to a factor of 10 gains in suppressing what we're not interested in and enhancing what we are interested in. So these are kind of incremental improvements on variables. So there it's really efficient for us. For anomaly detection, we don't really know yet because it was implemented in April, this strategy, which is a completely different way of selecting events, that we are the only experiment that does it, and we are just now getting the data in. So there we don't understand yet if there is new physics. But in terms of efficiency, for some tasks yet, for some are yet to be seen. So we have things, advanced pattern reconstruction tasks, where we currently use simplified Kalman filter-like algorithms that we are now trying graph neural networks for, basically like charge particle tracking reconstruction. And there it's to be seen if we can make it fast enough, because the latencies are so short.
Very cool, thanks.
Anyone else? Yeah, there's some.
Thank you for the very nice talk. You mentioned something about hardware design that you do together with the machine learning models that you develop. I know that usually it is a kind of long loop to do this. Can you describe a bit more how you manage to actually
that's why Aarrestad is so great. So it's just that now we can almost estimate everything in software. So what we work really hard, so the way it usually works is that you write this C++ code with your pragmas. And then you can roughly, with that code, you can estimate what accuracy you'll have. So that's kind of easy in software. But to get the final resources and latencies, then you usually have to build firmware, which can take a week. It can take a few hours or up to a week. So what we're really trying to implement is kind of predictive latency and resource costs. So the numbers I showed here that we do is just rough ratio. So you will save 80% of your space on your chip. We can do these kind of ratios. And now we are also doing symbolic regression to kind of predict from the size of your model, from the depth of your model, the number of neurons you have, et cetera, what's the activation function, what will the final latency be. And the way we do that is with surrogate models. We have a bunch of already software versions of a model and firmware. And we basically just do a symbolic regression trying to learn that function, basically, what will the latency be. Yeah, but then for like other testing that currently, where you really just want to know roughly what's the accuracy of the model, what's the latency, you can already do it in Python with these tools. Firmware is trickier.
I think there is also a hand raised there. Yeah.
Hi.
Hi, thank you for the talk. What are the theoretical limits of such speedups, and how do you address them?
The theoretical limits of such speedups, I guess, is just really the hardware.
So you just make better hardware, and that helps.
Hey, yeah, for us, yes, and also sometimes even in the so when you build firmware, every operation, you also want them to be physically close to each other. When you do another computation, it actually should be close to what you did before on the chip itself. So if everything is optimized, I think this would be your ultimate speed-up limit, is that every single operation that is done is as close as possible to what where the previous operation is on the chip in space. And then the size of the chip. And then you can, of course, speed up the clock speed of the chip, so how many operations that you do per second, but that also has then a bottleneck limit. At some point, the chip just says, no, I can't run this algorithm that fast. So size of the chip, where the algorithm is placed and routed.
And here in the middle, on the third row, there's one more question.
Hello. I'm very far away from sciences and physics, but it was very interesting speech for me. And I'm just curious, how often will be this hardware replaced or renewed there in the Earth?
Very seldomly. And for us, this is a question we often get from industry, because now you have cool engines, like Versal engines. There's cool computing. There's always cool new computing hardware to use. We have to budget far in advance for what we will purchase for such a system. It's very seldomly repurchased. Now, for this next upgrade we have in 2031, we are currently buying the hardware for that upgrade. So of course, engines and processors that's on the market between now and 2031 will probably accelerate fast, but we kind of have to make decisions very early on to be safe, that we can purchase all the 1,000 that we need. I said 500, but it's actually 500 plus 250 plus 250, so it's almost 1,000 FPGAs. And to have a guarantee that we have them, we decide very early on. Which is sad, because we can't really try new cool things, but it's safe.
But all the instruction which is underground will be...
No, the cavern stays. The experiment will actually be changed. We will reinstall big detectors. There we actually have cranes that lift stuff 100 meters up, replace, fix things, put them back down again. It's like a reassembly. For the FPGAs, yes, we take the elevator down with all the new boards, put them in, recable them. The cabling is the worst. And that's very seldom that we do. We do it in long shutdowns. So now the long shutdown will start end of next year until 2030, 31. Very seldomly. Reprogramming the firmware, we can do more often.
Thank you.
Okay, thank you very much. I think that's all we have time for the Q&A. And thank you very much for an exciting talk again.
Thanks for having me.